So today we're going to be taking a look at this. This is the HPDL-1414. Let's come in a little bit closer so you can see it because it is small. So what is that, like 10, 20 millimeters? Is that right? Maybe 10 millimeters, I don't know. So this is like a 4-character display, a smart, I can't do the fingers because I'm too zoomed in, but a smart display. So it's alphanumeric, which means you can show digits like numbers and letters. And I think it's got some kind of memory in here, so it knows the digits that you want to display, but we'll have a look at the datasheet in a minute, I think. And it contains all the LED drive circuitry, so I don't need to put resistors on these pins at all. It's all done internally. Now, so the Ascii decoder is the bit I don't really understand how it works in this. So I don't know how to drive it, essentially. So let's jump over to the datasheet and have a look. But before we do, I'll let you know what I wanted to do with it. So it's a 4-digit display, which means we can display some four-letter words. And I thought maybe it would be fun to make a rude robot, maybe, that uses all of our favorite 4-letter words. I don't know how many there are, really. But we'll make a little crap robot. It can certainly say crap on it. And this can be its head, maybe. I don't know what to drive it with yet. Maybe an ESP8266, but it'd be really nice to go with something a bit lower format size. No, what's the thing? Something with a smaller footprint is what I mean. But let's have a look at the datasheet and find out what we're going to need to do. So this is the datasheet, and I'm kind of hoping we're going to find some way of driving this. So what have we got here? So here's that reference to the RAM, the Ascii decoder, and the LED drive stuff. TTL compatible, so we've got low is 0.8, high is 2. End stackable, so you can put them end to end, which is nice. This is probably a bit small, isn't it? Let's come in a little bit. Absolute maximum ratings, so we're going to be fine with 5 volts, it seems. Here's our pinout. So we've got 12 pins, data input, write, digit select, data input. That's a lot of input. 1, 2, 3, 4, 5, 6, 7. 7 data inputs, 2 digit selects, and a write pin. What's that? 10. 10 pins, okay. All the digits on, we've got 70 milliamps. God, this is quite current hungry, isn't it? I suppose there are a lot of LEDs in there. 10 segments per digit, in fact. What else have we got? Okay, here's our timing diagram. That's good. So it looks like you set the address, you enable write by pulling it low, and then you throw in your digits and then pull write high again when you're ready. So probably nothing too critical there. Let's have a look. Are there any maximum times? No, any minimum times. All right. And here's our character set. How does that work then? So we've got data 0, 1, 2, 3, 4, 5, 6. So if we wanted to set an A, that would be 1, 0, 0, 0, 0, 0, 1. And there's a hex here as well. So is that the binary representation of the ASCII character? It might be. Yeah, that's basically how this looks like it's done. So you've got your address lines, the right line. So that configures which digit it's going to be. So 0, 1, 2, and 3. If it's low, low, it's digit 0. That's a lot of pins. I'm not quite sure about this. Hang on a minute. Let me just check something. Well, what do you know? Dave Darko has been at it before. 2015, in fact. So no surprises here. He's usually ahead of the game, ahead of the curve, whatever the expression is. So he's already been using one of these. What board is that? An Arduino Pro Mini. It's a really smart little device. You have 2 address pins, 7 data pins for the ASCII code, and 1 write pin. It is a code then. So you could literally just translate it across. Interesting. That's a lot of pins though. I was hoping to use an ESP8266. Don't know if I'm going to have 10 pins free. Oh, look, there we are. So it literally is that. So he's using a function here, setchar, that he's written. It takes a digit and the ASCII code, and then what's that thing called? Oh, I can't remember what that means. Anyway, what he's doing is he's just shifting that. He's using the byte, the literal byte, and then throwing it, the 0 or the 1 that it sees, on here, and then shifting that along. I can't remember what it might actually be called, shifting it along. I'm not sure. Anyway, we're not going to do that because I don't have enough pins. Let me go away and think about it for a minute. So it seems we're going to need to find something to do this with, and I've got a box here with a bunch of ICs in. Now these are all my CMOS ICs. I can't even zoom out far enough. Hang on a minute. Let's see if I can just shift it around. The lid will be against me, but so I've got a lot of different CMOS ICs in here that I dive into and use occasionally, and it sort of made me think maybe I've got something which will do the data lines potentially. Since it is just a decoded ASCII, maybe I can fake it in some fashion. So I'm going to have a hunt through here and see what I can find. It seems to me maybe I could use, I don't know, I'll figure it out. I'll find something, because we can drive 7-segment displays with CMOS ICs. So there must be something in here I can use. So I've got a couple of candidates here. We've got the CD4024, I think it is, and the CD4020. Now I think we're going to go with the CD4020. Now this is a binary counter as far as I remember. I've never used it before though, so it'd be interesting. Should we zoom in a little bit? I don't know if it'll be in focus, maybe. Yeah, one of these, we'll use this thing. Let's have a look at the datasheet for this, because God, I don't know how to use it. So this is the candidate, the CD4020. This is a ripple counter. Basically, it counts out in binary. So it's a 14-stage one, so we're not going to need to use all of these unbuffered outputs. So I don't know if we can... hopefully it'll work. Anyway, we won't need to use all of them, so we'll connect to the first 7. And the idea is that we can then pulse the input line. We'll get our binary output on here. We'll set the write flag to low, and then we'll reset this, and then we'll start again on the next digit. So we're going to have reduced, so we'll only need 2 pins instead of 7, I guess, for the data input. Yeah, that could work. How fast is it? Let's have a little look. Speed. Input pulse frequency. Okay, so that's a lot faster than I need it to be. That's cool. Don't know about input pulse width. How am I going to measure that? I could get the scope out if I know how to use it. Okay, this might work, maybe. Let's jump back to the bench and figure out how many pins we actually need, because it would be ideal if I wasn't constrained to something with more. Like an AT-Tiny85 would be great, because it's just such a tiny footprint. It would be really good to be able to make a board with an AT-Tiny85 on it. But I guess then we're limited to stuff that's programmed in. But that might be okay. Don't know. Let's jump back to the bench. Right, we might have a little bit of a problem. While scanning that datasheet, I did realise that the 4020, unlike the 4040, doesn't have all of the outputs here. So we've got... I didn't read this carefully enough, and I noticed that Q1 is next to Q4 there. There's no Q2 and 3. And why is that a problem? Well, when we count out in binary, what we really want is it to go 1, 2, 3, 4, 5, 6, 7 to give us our outputs. So what we're going to have to do, we'll have to do this in software, is increase the number of pulses by bit shifting our input int or whatever we're going to do. We'll try and figure this out later, but what we're going to do is go from Q4 down to Q11, I guess. So is that inclusive? I don't know. We'll figure it out. So we're going to have to start wiring from Q4 rather than Q1. That'd be interesting. Right, I'm going to get this wired up. So I've ordered some CD4040s, but I couldn't find one in my box, so I don't have any. So we're going to have to just make do, I think. I've just put this chip down on the board and trapped the wire underneath. That was clever. Well, that hot mess is done, I think. So down here we've got the right flag here, the right pin. Next we have address 0, then address 1, and then we've got our pulse in and reset just there. So we need to go and program something. Let's go do it. So let's do some coding. So I think there's going to be some pretty boring setup bits here. So let's just figure out how many pins we need. We'll do this above setup. So we're going to need a right pin. We're going to need the address 0, the address 1, the pulse pin. Oops. So that's going to go to our 4020, and we'll need a reset pin as well. So I'll set up these values and speed it up so you don't have to watch the boring bits. Now we need to set all of these up to be outputs, and then we'll probably set some default states in for when it boots up. Let's jump and look at the timing actually. Where is that? That's here. So our right pin is high, and when it triggers low, that's when we actually write to the display. So we want it as a default high, it looks like. And we probably want to pull our reset pin low as well. Not as well. I mean, just pull it low. Now, next up, let's create some variables for our text, shall we? So let's have a string. Go string. And that's going to be... Should we have the alphabet and go through it? Yeah, let's do that. Now in our loop, we probably want to measure the string length, because we only want to use 4 of those characters, I think. So we'll say, oh, we need a variable for that as well. Int string length. Oops, don't need a capital. And we'll start it out at 0. And then in our loop, we want to say string length equals go string dot length. So that's going to give that integer the length of the string. So it's going to count the number of characters. We probably want to record where we are in that string, because if we're only going to have 4 of these characters, then we need to know where we're starting to read from. So let's create another integer, which will be, what, string position? String pos will do. So string pos equals 0, and then we need to loop back, don't we? So, okay, so if we say if string pos equals string length minus 4, because we've got those 4 characters on there, then string pos equals 0. So we'll go back to the start, but we need to iterate through this and move it along. So else string pos Yeah, that seems about right. Let's give ourselves some space at the bottom here so we don't have to be all the way down there. So that's going to iterate through. We're not doing anything yet with the display, are we? So we probably need to write something. Actually, first off, let's figure out how we're going to get the integer, the decimal value of our text up here. So if we do, can this be in the loop? Yeah, I guess it can. Int digit equals go string dot char at, and then if we say string pos, yeah, we need to know which digit we're drawing as well, actually. So if we just leave that one as its string pos at the moment, let's just compile that because I'm not sure that's going to work. Oh, I need to save it. HPDL-1414. Oh, there's an extra thingy in there. Let's just... well, that compiles fine. So I didn't need to cast it, which is good. I thought I'd have to do, potentially have to do a cast like that. In fact, we can. It doesn't really matter. We can leave it as that. We know we're also going to have to probably shift this, but let's get the rest of the stuff done first. We should probably create a function, actually, because then we won't have to... We can pass this in the function, I think, can't we? So let's create a function. We'll call it digit right. We probably need to have just, it'll be an int, that's fine. And then we need to add in some variables. So let's look at what kind of variables we might need. So probably the digit we want to draw, so the position digit perhaps, and then we're going to have to sort those address lines out. So okay, let's do that. So if we say int digit, oh, that's not int digit number, and we need data for the add 0 and add 1, so we can change those. So let's say int data 1, sorry, 0, and int data 1. So those are our variables that we'll be pulling into this function. So let's start with that digit num. I think that's going to be important. So let's copy that. We don't need that up here, do we? Let's take it away. So let's put that in here. And then we can do the char at with an addition on there. Okay, yeah. Okay, so if we do that with plus digit num, so that way when we call this, we can say digit right, like number 1. It's this not going to draw number 1. I just mean it would be the next one along in the sequence. So it would have 0, and then the next one would be 1 and 2 and 3. So it will draw out crap, hopefully. So yeah, we'll do that. We're going to have to shift in a minute, but I'm not quite sure how to do that. So we'll figure that out in a minute. We want digital right, add 0, data 0. So those will be, oh, that could be a Boolean, couldn't it? They don't have to be those. And then we need add 1 and data 1. So these are our address lines. Next up, we probably need to, should we reset the, yeah, let's reset the 4020. So let's digital write it. We could do this in another function actually, but we won't bother. Next up, we're going to need to go through each one of our digits, I think, and pulse that 4020. So how are we going to do that? So we know what the number of our digit is. It's in that int at the top. So if we stick in a for loop, in x equals 0, and then x is less than digit x plus plus. There is a high probability that I've not done this correctly because I haven't written a for loop in ages. And then we're going to want to do some digital writing on the pulse pin, aren't we? So let's copy. Actually, we've copied both of those. So pulse and pulse. So we want to ping it up and down. We probably want to put a delay in there. So delay, we'll go for microseconds. And just 1. And then we'll do the same at the end there. So that is going to ping the 4020 for as many times as that int digit says. Then we need to set up our write pin. So actually we've done it up here, haven't we? So let's take our write pin and set it to low. And then we'll do another, we'll delay 1 microsecond and then set it back to high, I think. And then once we've done that, we probably need to do that shift thing. Now, how do you do that? We're going to need another variable, I think, because we're going to have to change digit. Yeah, okay. So int shifted digit equals digit, and then to shift it, was it, or is it the other way? No, we want it to go in the direction of those arrows, and we want to shift it 3, and that should take us onto that Q4. So if we have a look at the 4020 again, just here, oops. Is that the 4020? No, 4024. There we go. You can see that we start on Q4, so we need to shift this along a little bit so that we can get the right data. It does mean it's going to take longer to carry because we're moving up that, moving up those dividers essentially, up that binary count, but it should still be fairly quick. So once we've shifted it, we need to now use that digit instead. So we'll use shifted digit, and then that's close to it, isn't it? Oh, we need to, we probably need to start using the function, don't we? So let's do that. So digit write, and then we're going to say, we'll do digit 3. We need to have a look at this to figure out what the code is for selecting the digits. So we want digit 0. I think it reads that way, so 3 is the first one, maybe. So low, 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 high, high, low, high, high, low, low. I'm going to stop saying that now. All right, let's jump back and do that. So it was low, low, whoops, low, 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 high, high, low, and then high, high. High, high. Oh, God. And that should be it. I mean, it sort of looks right. Let's compile. If it does, it does. Okay, I'm going to go and grab an Uno, and I'll just double check these pins. I don't know if I tried to do, like, if you read the Uno on the opposite side to the analog side, then those pins should all be in line, I think. Just caught myself with a little error there. I'd forgotten to change these. They were all 3 before. A bit annoying. So hopefully we'll be able to see this working. I'll just upload it to an Uno and we'll plug in some LEDs. I won't do the display just yet. There we go, all wired up almost. We just need to pop some resistors in for these LEDs. So what I've done is connected the output lines from the CD4020 to some LEDs so we can visualize the output. Now I've also changed what the output's going to be so that we're only seeing A, B, C, D. So I'll go through the whole alphabet. I just want to make sure that A is correct. Now A should be 1 0 0 0 0 0 1. So we should see 1 at each end, and if we do, then I'm fairly confident it's working. We can plug the display in. God, wouldn't it be nice to get some LEDs with resistors built in? I don't know if that's a thing. There we go, all plugged in. Hopefully that one looks a bit dodgy, but there we go. Let's power it up. Okay, so I want to see 1 0 0 0 1. So that's A, that's B, C, D, A. Oh, I don't know if you can see them. There we go, C, D, and then A is 1 and then 1 at the end. That looks right to me. I've added a delay of like 2 seconds in between each digit. So I might leave that in there because it would be visually quite good to see. All right, in fact, we can do this now. Let me go and grab my phone so we can figure out what the pinout is. All right, so there's our pinout. So we've got 0, 1, 2, 3, 5, and then 6 and 4. Okay, so with that in mind, is that looking weird on the screen? It is a bit, isn't it? I'll move it away. So we'll take the very first one. So that's this black wire here, and we'll go over to data input 0, which is pin 8. We'll take the next black wire. That goes to pin 9. Oops. The next one goes to pin 10, and then one more from this side. It goes there. And the last one is pin 6, so we'll wait for that one. And then pin 4 is the second one in from here, so it's pin 2. Pin 2. And then 5 is the orange one. And then this one must be 6. Okay, let's power it up. Oh, we've got something on the display. Not sure that's the something that I want it to be. That does not look right. Just move some of these out of the way. That isn't right, is it? Oh, nuts. What's gone on there? Let's have a little look. What was it? A, B, C, D. So we've got an exclamation mark instead of A. Okay, back to the computer quickly. So, exclamation mark instead of A. Fantastic. Where is the ASCII table? So A, we wanted 1 0 0 0 0 0 1. Hang on a minute, we saw that. That is exactly what we saw on the LEDs. What's the difference between A and an exclamation mark? 1 0 0 0 0 1. 5 and 6 are the wrong way around. Okay, back to the bench. So it looks like 5 and 6 are the wrong way around. So what I thought was 5 is a 6, and what I thought is 6 is a 5. It's just not very easy to read on this data sheet, so they are switched around. So that is a 5 and that is a 6. So if I just focus on this, and then we'll do this live so you can see. Focus enough. Orange wire to here. I think that will be it. It's going to be a bit in the way, isn't it? We'll feed it across. Well, there's our... There it is. So A, B, C, D. Hang on a minute. Let's... Do they come up in the right order? No, it's writing back to front. I've done that wrong. It doesn't matter that it's writing back to front, but it works. That is fantastic. So I'll be able to do it with an ATtiny85, it seems. So I've just got the 4020. I think I'll get a 4040, then I won't have to do this weird bit shifting thing, but that means I can write anything in there I like. Anything I want at all. It looks so cool. I can't wait to build a little robot with this thing. Look how good it looks. I don't know if you can, oh,